Hello everyone, and welcome back to CS 11737 Multilingual NLP. Today I'll be talking about improved modeling learning methods for sequence labeling and classification. So in the previous class we talked about text classification, which is any set of a wide variety of methods that take a given input text X and predict an output label Y, including topic classification, where we classify text into food or music or topics like that. Language identification, where we take a text and predict its language, or sentiment analysis on the sentence document level, where we take in a sentence or document and try to predict its sentiment. And there's, of course, many others. We also talked about sequence labeling, where sequence labeling, given an input text X, we predict an output label sequence Y of equal length, including part of speech tagging, lemmatization, morphological tagging, etc. So a model that we looked at was a simple and standard model for sequence labeling or classification, namely bidirectional recurrent neural networks, where we look up word embeddings for each of the words in the sentence, and then we run an RNN, maybe in the forward direction and the backward direction. We take the outputs from the RNN, and we use this to make some sort of prediction on each word. However, while this method is conceptually simple, there's a number of issues with it. Specifically, the RNN model itself may be insufficient or perhaps inefficient in learning. And there are alternative models, such as bag of n-grams or CNN models, which we'll talk about this lecture, or self-attention or transformers, which we'll be talking about in future lectures. There's also rare words. And this is especially a problem in languages with richer morphology than English, and these can be difficult to learn. And some solutions to this include character-based word embedding, subword segmentation. Another issue is little to no labeled data exists for many languages. There's a lot of ways we can address this issue, and it's actually one of the important issues in multilingual learning. And ways we can do this is through unsupervised learning or cross-lingual transfer. Finally, labels tend to depend on each other, and predicting them independently is not efficient, and we can use structured prediction algorithms such as CRS. So the goal of this lecture is to kind of give a somewhat high-level overview of all of these ideas, and then if you're particularly interested in any of them, we'll provide references for you to take a look at. So first, I'd like to go into alternative sequence models, namely bag of n-gram models and convolutional neural networks. So one issue with recurrent neural networks is the issue of vanishing gradients. So let's say that we take an RNN model and we want to make a prediction about the class of a particular text sequence. Like let's say it's a sentiment label like positive or negative, or let's say it's a language label like English or Dutch, for example. So we have a label at the very end. That's what you can see at this little L loss function over here. And so we run our inputs through the RNN. And finally, in the end, we predict the label. And then when we do backpropagation, like we talked about in the last lecture, we pass the derivatives of this loss function back through the sequence all the way to the beginning. Now, an issue with this is RNNs, recurrent neural networks, have a problem of credit assignment. And what this means is basically they have more trouble than some alternative models in figuring out which of the words in the original sequence actually contributed to this loss function at the end of the sequence. And because of this, they can be particularly bad at learning, for example, from long sequences with weak supervision. And one of the reasons why is essentially you're running each of the inputs through many nonlinear transformations before you get to this final loss function, and this can essentially dilute the gradient or cause it to be lost during training. So there are alternative recurrent architectures such as LSTMs and GRUs, long-term memory and gated recurrent units, and these provide solutions, but they're still indirect in a way. So an alternative that you could think of using is something called a bag of n-grams. And So if we have our input sentence, I like these pairs, the way the bag of n-grams works is essentially it looks up an embedding for each of the multi-word sequences in the input sentence. So we have all of these unigrams here, which are I, like, these, in pairs. Then we have I like these pairs. I like these pairs, etc. We then take all of these, and for each unigram, bigram, and trigram, we look up an embedding, and then we could use this embedding, maybe add together a bias and get some scores, or maybe a representation for the sequence and make predictions. So these models are, in a way, more direct than those recurrent models, because, like, let's say we had a word in the beginning of the sentence or the second word in the sentence that is very salient for predicting, say, sentiment, like. If this is the case, if we use this bag of n-grams model, essentially it will pass the second word in the sentence onto the prediction just as directly as it would pass any of the other words in the sequence. So this is an advantage. It gives a much more direct modeling, and we can also model, I like these, or I like these as these short sequences, and this allows the model to basically pick up on these things that could be useful. One issue with a bag of n-grams model, however, is there can be a huge number of parameters. So if we count up all the multi-word sequences, like let's say we count up all the word sequences up to 4 or 5 words, there can be a very, very large number of these, exponentially large, essentially, if we run this over a large corpus with a large vocabulary. So an alternative to this method, and so sorry, the very large number of parameters can be problematic for a couple of reasons. One is just, memory consumption, disk space consumption. Another reason is because if these are sparse, if they don't appear very many times, they can be hard to learn. So a solution to this is convolutional neural networks. And convolutional neural networks, essentially what they do is they also consider multi-word sequences. So in this case, I'll give an example of 2-word sequences. And over every multi-word sequence, they run an identical function where they take in, for example, the embedding for the first and the second word, multiply it by a weight matrix, and add a bias, do a nonlinearity, and extract features. And then they move on to the next multi-word sequence and run exactly the same function. The only thing is that the inputs are different. Now it's the second and third words and the third and fourth words. So an important thing to notice here is essentially these multi-word sequences are kind of like soft bag of bigrams. So they're not explicitly remembering the features for I like these, or these pairs. But what it's doing is it's training a feature extractor, namely a linear transformation and a nonlinearity that you apply to all of the n-grams. And this allows you to essentially learn the important or salient features from them in a hopefully more parameter efficient way. We then combine these together. This can be done in an operation called pooling, where you take like the average or the max of all of the features over the sequence, and then you feed this into a predictor like the softmax and get probabilities. So the advantage of this is this can generalize better than bag of n-grams. So for example, if you had the word like, you could extract features from the word like, but also if the embedding for like is similar to the embedding for love or other kind of positive sentiment, I guess, verbs, then that would allow you to share parameters between these. And, if pears was similar to apples or oranges or other plural fruits, you would also be able to share parameters between other things that are regarding plural fruit, for example. In addition, you can compose multiple layers, so you could, combine together multiple layers together. And this is also better than, for example, LSTMs or other recurrent neural networks in some cases, because for the same reason as bag of n-grams. Essentially, it's a more direct modeling path that passes information directly into, for example, classification decisions that you're interested in. The disadvantage is that it is less direct than bag of n-grams when remembering individual n-grams is important. So, if you have individual n-grams that are particularly salient and there's not many parameters that you could be sharing between them, then maybe bag of n-grams is a better choice. So the next topic I'm going to talk about is modeling vocabulary items in a better way. So what we need to do in CNNs or LSTMs or any of the models that I've talked about so far is convert words into vectors so they can be fed into our sequence model. And each word independently gets its own vector representation. So what we've been doing up until now, we've been doing lookup, where we essentially look up a different vector for each word. And standard lookup entails basically taking a large matrix where the number of columns is the number of words, and the number of rows is the vector size. And then if we look up, say, the second word in our vocabulary, we will pull that out and use that in our downstream task. However, this has an issue of unknown words. So we can't have every single word in our vocabulary, or we can't have every single word in the language in our vocabulary, because we won't have all the words in the world in our training data. And, of course, because of this, we won't be able to have them in our vocabulary when we train our model. And, even if we had a huge training data, new words are invented all the time. So you won't be able to have this practically. Another issue is that larger vocabularies require more memory and computation time. So if you had a huge vocabulary, you would never be able to fit that in your GPU or something like this. So common solutions to this issue include a frequency threshold. So you kind of take all of the words that you find in your corpus, and you filter out the words with frequency less than or equal to 1, or maybe you do a rank threshold. So you find the top 50,000 most common words, and you keep all of them, and then you throw out all the rest and make them unknown words. However, this can be a really big problem, of course, because when you get one of these unknown words and it's important for you making the decision, you just lose that information from your model entirely. So there's a couple solutions to this. Oh, and one thing I should mention with respect to unknown words is this is particularly the problem for example, morphologically rich languages, where a single lemma can correspond to many, many different words just because you conjugate in different ways. So there's a couple solutions to this unknown word problem. One solution would be fully character-based models. So the basic idea is, instead of considering words, you just encode characters for the entire sentence. So what you do is, instead of splitting on word boundaries, you split on just every character and maybe turn spaces into underbars. You throw that into a big sequence model and extract your output. So this is, extremely attractive in theory. It allows you to do something very, very simple, and nonetheless, if you had a sufficiently powerful model, it should learn to be able to read these characters. After all, we humans are able to do so. But some issues in practice are this can be extremely slow. Your sequences become very long. So if you have a sequence model that takes a lot of time per individual input, it can be hard to train. And also, I found that essentially when you run these models, they can be hard to train. They just are harder to extract the salient information you need from the data that you have. So another very popular method that is used very widely now is subword segmentation. And basically, the idea is to separate rarer words into subwords and then embed them. So if we have this sentence, these are some subwords, where subwords is a relatively rare word here. We would segment it into, for example, these are some subwords. And so now our sequence, it's not anywhere near as long as it would be if we segmented into characters. I think there's probably 25 or so characters in the sequence, where there's only 6 subwords. But nonetheless, we were able to convert this into word and sub and s, which all are kind of common symbols. We then take this and we throw this into our sequence model and get the output. So how do we do this segmentation? There's a number of ways. One way we could do it is through supervised word segmentation, where we segment according to some linguistic criteria. There's a number of segmenters like Jeba for Chinese and Qt for Japanese. Or you could use morphological analysis if you have a morphological analysis tool for your language. So even if words are segmented with white space when you're writing, if you have a very morphologically rich language like Turkish or something like this, you could still use a morphological analyzer. Another very popular option nowadays is unsupervised segmentation, where essentially we use data-driven algorithms to discover which units to segment. So unsupervised subword segmentation algorithms, I'll give just a few examples. Byte pair encoding is one popular example, and what you do is you first segment the entire sequence into characters like we did before, but then you do an iterative process where you merge the most frequent subword sequence for a fixed number of operations. So if you looked at English and you found that the most common subword sequence was, character sequence was, for example, TH, you would merge T and H together into a single subword. And then if you found later that TH and E tended to co-occur a lot, which they should because it appears in common words like the and there, you would then merge TH and E together. And you would do this for a certain number of times, say 10,000 times or 20,000 times, till you reached your desired vocabulary size. There's also unigram-based segmentation, and the way this can work is essentially you create a vocabulary of the most frequent character engrams, and then you use the EM algorithm, the expectation maximization algorithm, to optimize the probabilities of a simple model, probabilistic model over these unigrams, and remove subwords with low probability. And references for both of these methods are included on this slide. And importantly, both of these are implemented in the very popular sentence piece toolkit, which you can download and use to train any of these models and then run them to segment text that you want to process. So subword segmentation is extremely simple, very useful, and I think that's its main benefit. It's just pre-processing, so you can run it before you even run your models, and it's fast and somewhat effective. However, it has a number of cons. The first con is that it only works when you can get the information you want through segmentation. So as we've discussed in the previous classes, there's a lot of morphology that's non-concatenative, which means that you can't simply get it by segmenting. So you can see here we have goose and geese. This is an example of one of the rare examples of non-concatenative, essentially transformations to words in English. But as we spoke about before, Hebrew and Arabic have this be a very common feature of their language. So if you use splitting, you would essentially be breaking apart words in an undesirable way. Another issue is when trained multilingually. So like, let's say you wanted to run this subword segmentation on different languages at the same time. Under-resourced languages or less resourced languages will be given fewer subword units. And the reason why is simple, or is kind of obvious if you look at the subword segmentation algorithms. Both of them are essentially relying on the most frequent subwords to be the ones that they do not segment up into smaller bits. So because of this, if Arabic, for example, had less training data than English, then it would get fewer subwords, and as a result, the segmented sentence lengths can become very long. Like you can see there's several sentence lengths of up to 100 for Arabic, where there are very few for English. So this blog post is very nice. You can take a look at it to read more about this issue. And finally, there can be inconsistent segmentation across languages. So if you have different languages that have very similar words, but with slightly different spelling, In some cases, it might be split up into two pieces, where in other cases, it might not be split up. So another option, which I think is a nice one, if you don't mind doing a little bit more work on the modeling side, is Subword-based embeddings. And the way this works is you have a two-level embedding. You first go from characters to word embeddings. So you take your characters, you run them through a character model and get a embedding for that particular word. And you do this for all of the words in the sentence. And then after you've done this for all of the words in the sentence, you go from word embeddings to sentence embeddings. So this has a number of nice features. Basically, number one, it's working on consistent word boundaries. So each of these embeddings will correspond to a word, and words are kind of, some basic units of meaning in a lot of languages. So morphemes are the actual basic units of meaning, but at least words, have some consistent meaning in general. And the other advantage is that this much longer sequence now becomes a shorter sequence before you run it through your word model, which can be more efficient as well. So there's a lot of subword-based embedding models, for example, Bi-RNNS or LSTM models, convolutional neural network models, and bag of n-gram embedding models. I've tried all of these in my work, and my impression is that in this case, the more direct methods tend to perform better. So bag of n-grams work better than CNNs, which correspondingly work better than BiRNNs. And I think the reason why bag of n-grams works so well for character-based models is because there really usually aren't that many characters in a language, which means that even if you memorize n-grams for all of them, you can still do a pretty good job of learning the parameters, and they don't get too big. And also, bag of n-grams are used in widely used tools, such as the fast text word embedding toolkit. So I'd like to also introduce a piece of work that we have done. It's actually by Cindy, one of the TAs in this class. And we essentially create embeddings specifically tailored for cross-lingual learning using a method we call soft decoupled encoding. And the idea is basically we have a number of desiderata for cross-lingual lexical learning. So for example, spellings are similar in many languages, like English and Spanish. The word Madrid would be spelled the same way in both. However, there are also some consistent differences. So in English, the word revolution is spelled T-I-O-N, whereas in Spanish, it's spelled with a C and an accented O. And some words are completely different. For example, in English, the word hand in Spanish is the word mano. So we came up with a model that essentially takes these intuitions into account. And we first start out with a bag of character n-grams. So this handles the spelling similarity part. We then have a language-specific transform. So like English would get one transform, linear transform, Spanish would get another. And the idea here is to model these consistent spelling differences. And then finally, we have latent semantic embeddings, where essentially we pick out from a library of embeddings which embedding we should be using and add that together to the transformed bag of character n-grams embedding. And this is to take into account the fact that some words are completely different, but might correspond to the same underlying semantic concept. So I like this work, number one, because it's effective, but also because it demonstrates in a way how you can kind of specifically design models that take into account your intuitions for how cross-lingual learning should be happening. So I highly recommend taking a look at this paper. So now I'd like to move on to the next topic, unsupervised learning of representations. So the motivation for this is we often have very little labeled data for most analysis tasks for most languages. And one solution to this is that we have semi-supervised learning, where we also learn from unlabeled data. And there's a couple of types of semi-supervised learning. The first one is the learning of the neural feature extractors that we use in our downstream task, but train them on a different task, such as language modeling. And another is learning of the actual output predictor as well. And the way you can do this is form a generative model based on the outputs and train that generative model. So I very much like both of these topics, and we've published papers on both of these topics, but the former is significantly easier and more widely used, so I'm going to focus on it in the rest of this section. So the way we do this training is through a method called multitask learning. And multitask learning, essentially what it is training representations to do well on multiple tasks at once. And specifically, I wrote joint multitask learning. And the way joint multitask learning works is, I guess it's the at-once part in this explanation. So multitask learning doesn't necessarily have to be training on both at once, but joint multitask learning trains on both tasks at once. And the way we can do this, in general, is pretty simple. We form a model where we have an encoder that's shared between multiple tasks and outputs representations. So this could be, our standard sequence model like an LSTM or CNN or something. But we train it on multiple tasks where we sample one mini batch from each task, alternatively, or some other, scheduling strategy like that. And another very widely used and popular paradigm is pre-training, where we first train on one task and then train on another. So we first, maybe train our model on language modeling, and then we use this model to initialize the encoder of a downstream tagging task. And there's a number of objectives that we can use here, including language models, masked language models, or other methods. And I'm going to talk about both of these in the next few slides. So our first unsupervised objective is language modeling. And the way this works is basically we predict the probability of a sequence, so P of X, where X is the sequence we want to model. And this could be done, for example, by predicting the words from left to right. So we use the chain rule of probability and basically say the probability of our sequence is the product of the probabilities of the next word given all of the previous words that we predicted so far. And in a way, we can think of this as like a sequence labeling or tagging task, where essentially we have a unidirectional recurrent neural network, and we feed in the previous word, and as the tag, we predict the next word. So we feed in the beginning of a sentence symbol, we predict I, we feed in I, we predict hate, feed in hate, predict this, et cetera, until we get to the end of the sentence and predict the end of sentence symbol. So this is nice. This gives you a way of learning features, and it also, for example, would give you a way of generating text or other things that you might want to do with a language model. But the disadvantage of this objective is that because you need to predict words from left to right or in some other order like this, you can't use bidirectional context. So essentially when you're processing the representation for that predicts the word this, you don't have any information about the following word, movie. So a second unsupervised objective that also has lots of popularity is masked language modeling. And the way masked language modeling works is by using a technique called denoising autoencoding. And denoising autoencoding in general is a method that's been very widely used in computer vision, NLP, other areas. And it essentially consists of doing some process to take clean data and add noise to it, and then taking the noise data and re-predicting the clean data. And in the process of doing so, you learn kind of about the features of data. Because to denoise the data, you need to learn about the features of what natural data looks like in order to do that successfully. So in natural language processing, masked language modeling is a typical example. So essentially what masked language modeling does is it corrupts the input by taking some of the inputs and replacing them with masks or replacing them with other words in the vocabulary, and then using the features that you get out of this featureizer to re-predict the missing words. So to, for example, re-predict hate or love in this example. So the advantage to this method is that now you can easily use bidirectional context. You could use any featureizer you want, such as bidirectional LSTM or CNN or transformer or whatever. However, the disadvantage of this is not actually a language model, because in order for something to be a language model, to be something that can predict the probability of a sentence, you generally rely on the chain rule of probability like I talked about before, and now you're not predicting from left to right, and this kind of assumption breaks down. So these models cannot easily do generation or sequence scoring. So you can do generation or sequence scoring with them with a few tricks, but it's not as trivial as using a regular language model. So when there's a lot of popular language models like this now, including many multilingual models that can do feature extraction for you and greatly improve your performance. These methods are often called things like BERT or MBERT, Multilingual BERT, XLM, XLMR, Unicoder, etc. And the people who create these methods often also release pre-trained models. But when you're talking about these models, they usually refer to a combination of the model, which is the underlying neural network architecture, the training objective that was used to train it, data, what data the authors chose to train the model, etc. And one thing that you should remember is that these are often conflated. So people will say, oh, MBERT is better than XLMR or vice versa. But in fact, very often it might be several things that differ between them. It's not just the model, but also the training objective and the data that it was trained on. So what I'm going to try to do in the next few slides is break down some of the popular multilingual pre-trained representation models based on these axes. So BERT is kind of it's not the first pre-trained model, but it's certainly the most popular and the one that really, started the boom in this area, or, made the boom in this area popular and long-lasting. So the way it works is basically it uses a self-attention model, and I'm going to talk about self-attention in basically 3 classes. But you can just think of it as a sequence featureizer, if you'd like, bidirectional. And then you input a sentence or a pair of sentences, and you also add a kind of dummy token at the beginning of the sentence that can be used for text classification, etc. It uses subword representation, so it might split playing into play and ing. And it uses a masked language modeling objective and also does next sentence prediction. So essentially it predicts whether the next sentence in a sequence is a natural next sentence or not, or one that's sampled randomly from another document. And it was trained on books corpus and English Wikipedia, so it's essentially an English-only model. But because this is multilingual NLP, English-only models are kind of boring for us, so let's talk about other models as well. So there's also other monolingual BERT models. So BERT has been trained in many languages, and some of them have kind of clever names, such as Camembert for French. So if you want a model for a specific language, it is quite possible that these already exist. But perhaps a more popular model is the multilingual BERT model. And essentially it's the same model as BERT, but it's just trained on many, many languages. So the first thing you have to do is create a subword vocabulary. And the way the subword vocabulary works is it uses kind of byte pair encoding style method, but it's trained over all of the languages jointly. And when doing so, in order to prevent the lower resource languages from getting no subwords at all, they slightly upweight the low resource languages in the learning of the subword vocabulary. The training objective is the same as BERT. It's just basically BERT, and it was trained over 100 languages worth of Wikipedia data, so you can use it for many different languages. one thing I'd like to point out is the results were quite impressive. You would be able to do things like train analyzers on very few data points, or maybe even no data points in some languages, and still be able to get pretty nice results, especially if you train, for example, named entity recognizer in English and transferred it to a new language. Another example is XLM. So XLM, the model is a self-attention model, the same as BERTS, Subword representations, etc. But it was trained with a masked language modeling objective that used not only individual or sentences or sentence pairs from the same language, but also sentence pairs from different languages. So it was trained on parallel data. And it was trained on multilingual Wikipedia with the regular masked language modeling objective, and also on parallel data from like UN, Europarl, etc. And the idea here is that, just training multilingual BERT on a single monolingual data is less likely to be able to learn good alignments between the languages for cross-lingual learning, as you would be able to do with if you had explicit signal from this parallel data. And another model is XLMR. So this has also been released. And basically the model, again, is the same as BERT. The objective is actually the same as MBERT, and this is a slight misnomer, because as far as I can tell from reading the paper anyway, it does not use cross-lingual data like XLM. So it's trained in a purely monolingual fashion. So the main difference from MBERT is mostly that it was just trained on larger data. So it was trained not only on Wikipedia, but also a whole bunch of web data from a web corpus called the Common Crawl. So then the question naturally becomes, which model should you be using in your work? And to help answer this question, it can be nice to look at multilingual benchmarks that try to compare different models across different languages and different tasks. So our XTREME benchmark, it has 10 tasks, 40 languages over things like sentence classification, structured prediction, sentence retrieval, question answering, many different languages with different levels of data availability. And there's many conclusions in the below cited paper if you're interested, but the success of this kind of pre-training a model plus cross-lingual transfer paradigm varies greatly between tasks and languages. And also, interestingly, different models are better at different tasks, which indicates there's kind of like a not one size fits all method for using these representations. Okay, so finally, I'm going to be talking about structured prediction models. And first, I'd like to talk about what do we mean by structured prediction. So basically, structured prediction is any prediction task where classes are too numerous to explicitly enumerate. So one example of this would be sequence labeling. And in sequence labeling, let's say we're talking about part of speech tagging, we have a very large number of sequences. Specifically, if n is the length of a sentence and m is the number of tags that we have in our vocabulary, we would have m to the n possible tag sequences that we would want to optimize over. And so we couldn't, explicitly enumerate all of those outputs. However, we can take advantage of the structure of the problem, in this case, that we are doing, we're labeling a sequence, and use that to take this into account. So for example, we might predict each individual tag separately and independently. However, the output tags could interact with each other. So for example, if we take a famous example from English, time flies like an arrow, we could come up with a number of different part of speech sequences for this sentence. So here are 3 examples. And each of these is actually a valid part of speech sequence for this sentence. So the first one is basically the interpretation that the actual proverb in English means. So time moves similarly to how an arrow does. This second one has a noun phrase here. So basically this noun phrase is something called time flies, which are some, bizarre variety of the insect fly, for example. And these flies like arrows, so they're fond of arrows. The final one would be a command form sentence in English. So it would be basically saying, please measure the time of a fly similarly to how an arrow would. However, if we tried to predict all of these independently and say took the maximum frequency of all of these interpretations, we would actually get something completely different. We would get a sentence with no verb in it whatsoever. And corresponding to the interpretation that time flies, the bizarre insect, are similar to arrows. So if we have a sequence labeler with a bidirectional RNN, and we predict each of the sequences independently, essentially, this is not a model that's exploiting the fact that these sequences should interact. So it's not modeling the kind of structure of the output and would potentially have trouble with examples where the output depends on each other, like the previous one. So one way we could fix this problem is essentially by taking in the previously predicted output and feeding this into the input, feeding this into the RNN that we use here. And what this would allow us to do is see that, well, last time we selected a personal pronoun, or a pronoun is the name, is the part of speech tag here. So because we selected a pronoun of the part of speech tag here, we're more likely to select a verb next, for example. So another option is to use a structured prediction model called conditional random fields. And these conditional random fields are very widely used in sequence labeling, so they're a good thing to know about. And in order to get into conditional random fields, I need to talk a little bit about local normalization versus global normalization. So essentially all of the models that I've talked about so far are locally normalized models, and these locally normalized models have each decision made by the model individually have a probability that adds up to 1. So this could include things like the tagging models or the language models that I've talked about so far, where basically for each position in the sentence, we calculate a probability of the next tag or word using a softmax function, and use that probability to calculate the probability of the next word. However, there's also another class of models called globally normalized models or energy-based models, where each sequence has a score which is not normalized over a particular decision. And then essentially what we do is we take these unnormalized scores and we normalize them over all sequences. So the issue with globally normalized models, and the reason why they're used a little bit less frequently than locally normalized models in neural networks, is because this normalization over all of the outputs is computationally prohibitive. So as I said before, if we have n to the m tag sequences, we would have to calculate the sum over n to the m tag sequences if we don't do something essentially more intelligent. So one example of an intelligent thing we can do is epitomized by conditional random fields. And conditional random fields are essentially a general form of globally normalized models that calculate feature functions that capture the interactions of outputs explicitly. And the way this works is essentially they directly calculate the score and then normalize over all of the scores to get the conditional probability of the output. However, this can be intractable. This, as I said, the sum down here could be an issue. So the more common variety of conditional random fields that we use essentially calculates the score as the product of scores between individual neighboring tags. So basically the score of tag 2 will depend on tag 1 and tag 3. and the score of tag 3 will depend on tag 2 and tag 4, etc. And we can calculate these within neural networks, and basically the way we do so is we run a feature extractor over the input and two neighboring tags, and we multiply this by a probability weight matrix to get the score for this transition. We also have features that only consider a single output. So this is kind of like what we calculate with our LSTM style, like our regular by LSTM style weight matrix times feature function plus bias in the softmax. So essentially the main advantage of the conditional random field is it's adding these transition functions here. And we can use neural features in neural networks by basically extracting these features according to neural networks for both the transition and the emission probabilities. However, this is a problem that this would result in a very large number of parameters if we had an individual transition for each of the features extracted by a neural network. So what's common to do instead is just have a single scalar feature for each transition saying how likely that transition is, compared to the other ones. And so just to kind of summarize this, and essentially you extract features from, for example, a bi-LSTM, and then you have this conditional random field kind of model on top of it that takes in these features and turns them into scores, which you can then use to optimize the problem, the scores here. And in order to train and generate outputs according to this, let's say you want to calculate the probability of a sequence to calculate, the maximum probability of the sequence or something like this. The probability of any individual sequence is relatively easy to calculate. We can just use, we can calculate each of these functions for each of the transitions and emissions in the sequence. The difficult thing here is how to calculate the sum over all of the sequences. And when training, we want to calculate this partition function itself in order to calculate the likelihood function to optimize the parameters. And when we're decoding, we want to calculate the maximum value here. So I won't go into the details in this particular presentation for the lack of time. But what you need to know is essentially it is possible to do this using dynamic programming algorithms. And I would suggest taking a look at the reference that I cited before, which explains exactly how this dynamic programming works. And the reason why this dynamic programming works essentially is because we have limited ourselves to this kind of linear chain CRF that only considers neighboring tags. And because of this, we can gradually step through the sequence considering all of these combinations of neighboring tags and update the probability of the partition function one step at a time. Okay, so that's all I had for today. I know this was a little bit dense, and we covered three important topics. Because we covered 3 topics for the discussion, what I would like you to do is I'd like you to pick the topic that seemed most interesting to you. And based on this, choose one of these 4 papers. The first one on subword models, the second 2 on unsupervised learning of representations, and the final one on structured prediction models. And for the paper that you read, what is one problem with a standard sequence labeling model that the methods presented or discussed therein resolve? And also, what is one problem that you think that the discussed methods would not be able to resolve? So one issue that would still stick out after you ran these models. So that is all I have for today, and thank you very much for listening.